Okay, hello everyone. Let's take a look at a curve sketching problem, which will involve finding critical points, inflection points, and identifying places where the function is decreasing, increasing, and concave up and down. So we have this function, x minus 1 over x here, and it's the difference between the linear function with the reciprocal function. So it's a smash between a linear and a rational function. In order to graph this, what we want to do first is the pre-calculus stuff, which is identify two key things for rational functions. What are they? The horizontal and the vertical asymptotes. So in case you don't know, in order to identify the vertical asymptote, all you really need to do is set the bottom of the denominator equal to 0. So in other words, x cannot equal to 0 in this expression because we cannot divide by 0 in the real numbers. So that's x equals 0 is a vertical asymptote. I call it vert ASMT. And now what about the horizontal asymptote? Well, we basically want to take the limit as x approaches infinity of this function here. And that, well, if we want to put this into a common denominator, that's the best way to do about this. X minus 1 over x, we can multiply that x by x over x by itself. So we get minus 1 over x. So this becomes x squared minus 1 over x. And that approximately just becomes x squared over x. We only care about the dominating terms. X squared is bigger, grows a lot more than x. So this thing is going to diverge and become infinity. So in other words, we have no horizontal asymptote. Right? Okay, let's go and write down this key part. Now we're going to do the calculus, which is take the derivatives of this function. VA stands for vertical asymptote here. In order to make this easy to differentiate, we'll convert it so that 1 over x is written in negative exponent form. So this will be x minus x to the negative 1. If you differentiate that now, you can differentiate the first term. Derivative of x is just 1. And for minus x to the minus 1, you apply the power rule, so that a minus 1 term comes out. And the x is decreased by an exponent of 1. So this just becomes 1 plus 1 over x squared. And now we want to go and see if there's any critical points, any local maxima or minima. Best way to do that is to set this equal to 0 and then solve. I can multiply x squared on both sides. So I get 0 equals x squared plus 1. But look out, this is the infamous equation where if we solve this, we'll get imaginary numbers. So therefore, x is not going to be a solution in the real numbers, so no critical points. Because we graph everything in the plane of R2. Okay, so that's all good. What about the inflection points though? Where can we tell that? And we can't tell from this, unfortunately, as a result, where it's going to be increasing or decreasing, because this requires a bit of complicated, complex analysis. Imaginary numbers can't be compared for inequalities. So this is useless for us. Let's take a look at the second derivative now. Well, we get that f prime of x equals this, 1 plus 1 over x squared. And let me rewrite it again as 1 plus x to the minus 2. We do the same spiel. by taking the derivative again, this will become 0. This will become minus 2, x to the minus 3, minus 2 minus 1. And so this is just minus 2, x to the minus 3. And here you might think, well, there's a negative sign, so this should be concave down everywhere. Be very careful. That's only true f prime of x is concave down only if x is positive. Because if that were the case, then f double prime of x would be a negative number. So say one example, we can take x equals 1, put it into there, f prime double prime of 1 becomes minus 2 over 1 cubed, so that's minus 2. But if I were to go and put in here x minus 1 on the other hand, then f double prime of minus 1 becomes minus 2 over minus 1 to the 3, and the negative 1 raised to an odd power is negative, so this is minus 2 divided by minus 1. That's going to be a positive number. So if x is less than 0, the function is concave up. And these are the most useful things we're going to get. So, to summarize, the most important thing we know is x equals 0 is a vertical asymptote. We also know for f prime of x equals 0, x is not a solution of the reals. It is in fact solution of the complex numbers or imaginary numbers. Just put imaginary number here. And for f prime double prime of x, if x is greater than 0, f of x is concave up. Concave down. Concave down. If x is less than 0, f of x is concave up. Now, we want to translate this into graphing our actual function. How does this work out? Let's draw the Cartesian coordinate graph over here. This is x, this is y. We know that there's a vertical asymptote along the vertical axis, so the function can never cross through this point over here. X equals 0. And that's good with us. If we know that if for negative numbers it is concave up, we know that it's got to have kind of a U shape, sort of like a opening minimum parabola, but that it's going to eventually reach y equals positive infinity as x approaches 0 from the right hand side. So this will become oh, sorry, I forgot a key thing. We actually need to find the roots of this guy. My apologies for that. Roots will also be useful. So 0 over here is going to equal x minus 1 over x. If we multiply x on both sides, we get 0 equals x squared minus 1. That's the difference of two squares. So 0 equals x minus 1, x plus 1. Therefore, x equals plus or minus 1. So we know that the graph has to pass through the horizontal axis at the points 1, 0, and negative 1, 0. Okay, so that's a part I'm missing. But it still has to go and obey this concave up U shape here. So it's going to look like this as a result. Didn't quite go through the points. And then what about from the right hand side? Well, if f double prime of x is positive, it's going to have to be concave down. It's going to have to be the opposite of it. It's going to have to be an upside down frowny face U shape now. So the best way I can draw that is it's going to look like this. And if you check on Desmos, that is exactly what the graph f of x equals x minus 1 over x looks like. So yeah, there's one working example. I hope that was helpful for you. Please feel to like, comment, and subscribe. So then, see you around.